Okay, thanks a lot, Tomáš, for coming. And yeah, the screen is yours.
Yeah, thank you for your introduction, and thank you everybody for waking up that early. So I will present you today joint work with Peter Brocho. He's on the picture on the left, and Ladislav Stacho, who is on the picture on the right. So at least you can see them, and I hope you see me on Zoom, so I don't have a picture of mine on the first slide. So let me start with some classical definition. My talk will be about flexibility, which is some variant of coloring problem. So let's start with coloring problem. So we say that we define a list assignment L for a graph, which is a function that gives each vertex a set of available color to choose from for coloring. And we will say that what is L coloring, which is a function which assign color to vertices in a way that neighboring vertices don't get the same color. So we have HUV, then the color has to differ. So you probably know all those terms, but I think it's good to start at the beginning. So, and of course, this color that we assign to vertices has to come from the lists we have for them. So every time I will be speaking about L coloring, I mean proper L coloring. So one of the classical notions in graph coloring from 70s or 80s is choosability, and there we ask if graph is k-choosable. We say that graph is k-choosable if for every possible list assignment of size at least k, there is some L coloring. And one last studied concept that I would like to mention on this slide is precoloring extension. And there is a question that we already precolored some of the vertices of the graph. And the question is whether we can extend this coloring of some vertices of the graph to the proper coloring of the whole graph. So let me now show you on the picture what flexibility is, or what is the motivation for flexibility. So on this picture, you can see a graph with list assignment of size 3, and that's our input. And then we can ask for list coloring. So by those circles, you can see a list coloring which satisfies this condition that for neighboring vertices you have distinct colors. So you can check all the edges, and that's nice. But in some problems, some vertices might have preferences. So here the preferences are denoted by those squares, and not each vertex do have to have preference, and also the neighboring vertices can have the same preferences as you see in this example here. So those are the preferences, and once we want to produce the coloring, it's better to produce coloring that satisfies the preferences. So the precoloring extension problem would be exactly question satisfy all the preferences. So produce the coloring which matches all the preferences. But as studying of precoloring extension tells us, it's usually very hard question, and most probably the answer is no in the reasonably difficult graph classes. So in flexibility, we relax this notion a bit. So now we would like to satisfy a reasonable amount of preferences, but we do not require to satisfy all of them. In particular, on this example, we of course haven't satisfied the preferences that are contradictory. But you can imagine that we are not able to satisfy even preferences that doesn't look contradictory on the first glance. So here is an example of some coloring that satisfies quite a lot of preferences, and for us quite a lot will mean a constant fraction of the original size of the preferences. So let's let's take this intuition formally. Let's take this intuition. Let's start to look at it more formally. So we defined what request is. So request is for graph and for list assignment L. It's a function that assigns those preferences to vertices, and we are allowed to assign the preferences only of those colors that are available in the lists. We cannot wish for color that we cannot get. And then we say that request is epsilon satisfiable for positive epsilon. And that means that there exists a list coloring phi of G such that phi of V, the color of V matches the request. And this happens sufficiently many times. So we match the color for epsilon times the domain of R, which is the number of vertices that requested the color. So this means epsilon is this constant for us. And last term, this is the central crucial term of what we are studying, is epsilon flexibly k-choosability, which we say about graph if for any list assignment of size at least k, and for any possible request, we know that we can satisfy at least the epsilon fraction. So every possible request on any list coloring is epsilon satisfiable. So as most usually, we are saying that some graph class is epsilon flexibly k-choosable if all graphs are. So this is the main crucial definition. So if you have any questions, feel free to interrupt me at any time. And if you don't have any questions, let me continue. So maybe you wondered why we are speaking about lists from the beginning and what happens for classical coloring. So in the terms of list, what happens if all the lists are the same? And for that, the answer is a bit disappointing or trivial. We can easily say that if the graph is k-colorable, then we can satisfy 1 over k of the requests. And that's best possible if you think about complete graph and you imagine this stupid situation that all the requests are the same, then we can satisfy only one of them. So fraction 1 over k is best possible, and we can achieve it by the following construction. So let me show you the construction now. So if we have k-colorable graph, then we can partition it into k independent sets. So those are those green boxes. But also in each green box, we can group the vertices based on their preference. So this first quadrant are vertices from the first independent set that requested color 1, and so on. Here they requested color 2, color 3, color 4, up to the vertices that haven't requested anything. So we will ignore the vertices that haven't requested anything because we don't need to fulfill any requirements for them. So we don't have to care about them. So one more thing, on this picture you can see that if we produce the coloring as suggested by those numbers below, then we satisfy exactly those requests of vertices on the diagonal here. And now by simple counting, we know that there is k factorial possible coloring of those independent sets. And if we look at it from the point of view of this one small box, then for it, k minus 1 factorial coloring are good. So as long as the first independent set gets color 1, then all other permutations are good from the point of view of this small box. And then if you compare those fractions, you will get 1 over k fraction, and then by pigeonhole principle or by some probabilistic argument like expectation, you will derive the statement.
So is it the same as saying that if you take any coloring and you randomly permute the colors, then every request is satisfied with probability 1/k, so then you can apply the linearity of expectation?
Yeah, exactly.
Okay, good.
Yeah.
Mm-hmm.
So that shows this, and it's a bit disappointing then that for classical coloring, it's let's say boring. But on the other hand, for list version, it looks quite complicated, and at least not some of the results haven't come very easy. So let's look at planar graphs. Those are the most explored in this direction. And let's recall the highlight result on planar graphs. So classical for coloring theorem. Of course, planar graphs are 5 choosable. And in terms of epsilon flexibility, they are 6 choosable. Or if we apply weights, I haven't explained how weighted flexibility works, but basically you can think of requests that are weighted. So one vertex can request many colors with some weights, and then if you do it straightforwardly, then you can derive a notion of weighted epsilon flexibility, and for that only it's known that list of size 7 works, but it's a big open question if you can do it better, right? There is no lower bound for flexibility known, so it can happen like no other than from choosability. So it can happen that those numbers are not 6 and 7, but they are 5. But it's one of the main questions here. So I said what's not known, but let's look at what is known. So on planar graphs, there is large couple of results on various subclasses of planar graphs. I should say that most of the results, like all those orange results, but also some of those originates in discharging method. So basically, there is tool how to develop reducible configurations, and then everything is done sometimes by a very elaborate discharging argument. So by this, the good bounds are done for triangle-free graphs and graphs of girth 6. Those 2 bounds matches what's known for classical choosability, so that's the best possible. And then there are some more bounds that are not the best possible, but they point in some direction. But maybe right now it's not important what the results. Okay, this is also the best possible. Now it's not so important to discuss the specific result, and I will return back to this overview a bit later. But first I would like to say different point of view. So this was point of view from planar graphs, but let's now take a look from point of view of degeneracy. So we say that graph G is degenerate if there is a vertex of degree at most D in every subgraph of G. We can equivalently think of it in terms of degeneracy order. So we will produce ordering of vertices in a way that each vertex has degree to the right at most D. So this is the first vertex in the order. Then second vertex in the order has degree to the right at most D, and we don't care about the degree to the left, and so on. So this is degeneracy, and from point of view of degeneracy, we can solve choosability by adding one more color, and it's easy greedy algorithm. So we can from the other side of the order, we can assign arbitrary color to the arbitrary color from the list to the very last vertex, and then we can look at the predecessor and again assign arbitrary available color from its list, which means we discard all the colors that are forbidden by our choices on the right. But as the degree on the right is at most D, then we discard it at most D other colors, and we are left with one more color. So in this easy way, we can greedily color our graph. If it's degenerate, then the +1 color is sufficient. But for flexibility, it's not the case. Dvořák Norin Postel showed that we can do this in more complicated way with D+2 colors. And that's one color more. And I will show later, it might be quite difficult question. So they conjectured that it might be possible, or it should be possible to do it with D+1 colors. But as I said, it don't have to be easy, and I will look at it on the next slide. So right now I will say that they also mentioned that it's a bit easier question for non-regular graphs of maximum degree D+1. So show the same, but for this restricted graph class. Non-regular means that there exists a vertex of degree at most D. So we can build those graphs are degenerate because we can start by this special vertex V, put it on the beginning of the order, it has degree at most D, and then if the graph is connected, because we care only about connected graphs, then we can take one of its neighbors, and now it has also degree to the rest of the graph at most D, and so on. And in this way, we can process the degeneracy order. So those non-regular graphs of maximum degree D+1 are degenerate, but it's a subclass of it. So now let's return back to what I promised. I said that this conjecture might not be easy to have the same for flexibility as is trivial for choosability. So let me now show you what proving this conjecture could mean. So this is the list of the known result for planar graphs, and I marked those that are. I wrote here the degeneracy of those graph classes that were shown there, and you can see that if this conjecture is true, then those orange arrows point to the results that would be implied by the conjecture. And even for D equals 2, this would still imply some results that were not the most complicated ones, but still it was not for free to show it. So it might be difficult to show this in general. Here I also wanted to mention that this suggests us which questions on planar graphs might be difficult, because, for example, planar graphs are 5 degenerate and 5 choosable. So it can be possible, as I mentioned, that they are also 5 flexibly 5 choosable, but it might be difficult because even for the classes that are implied by this conjecture, in some cases, let's say in those triangle-free graphs, it was very difficult to calculate the discharging. So here are other candidates which are not implied by the conjecture. So planar graphs of Girth 5 are 4 degenerate and 4 choosable, and C4 free graphs are also 4 degenerate or 4 choosable. So to sum up the known results, they are done by discharging, so they are not algorithmic. Which I would like to point it out because we provide algorithms for our results, which I will mention soon, and they are done by sometimes by very elaborate case analysis in discharging and creation of reducible configuration. So that's what's known, and now let me tell you what are our results. So we don't know. We cannot show the conjecture, but we can show this at least part. So we can show that non-regular graphs are actually degree +1 choosable. Are degree choosable, right? Because they are delta -1 degenerate. So this is our statement. We have graphs in slightly stronger form. So let me say it again. So if we have graph of maximum degree delta, then we will prove that they are 1/6 delta flexibly delta choosable unless they are k delta +1. This fraction 1/6 delta is up to constant best possible, because if you take two clicks of correct sizes joined by matching, then you cannot do better than 1/delta. So this constant is up to 6 it is best possible. So this I plan to show you this result in slightly easier form, because to get this constant it was quite more involved, but I plan to show you the proof of it with Morse constant. Also, one more result that we managed to show was for graphs of 3 with 2, and we showed that they are 1/3 flexibly 3 choosable. Again, this is best possible because of triangle. Like you can satisfy only 1/3 of requests on triangle. And here I am speaking about 2 trees. So 2 trees are H maximal graphs of 3 with 2, and as adding vertices to the graph makes only our problem more difficult, then we can just focus on 2 trees. Oh, I will be using terminology of 2 trees in our proofs. 2 tree is constructed as follows. We will construct it by induction. So we start with triangle, and then we pick arbitrary edge of constructed graph, and we add one vertex that's attached to edge, like here. Then we pick another edge, this purple edge, and then we add one vertex and join it as here. And again, two more, we pick this edge and created a triangle, and one last. So this is example of 2 tree, and we can build them nicely in this inductive construction. And this answer our previous question that we had with my co-authors, that what about outer planar graphs? And outer planar graphs are subclass of graphs of 3 with 2. So by this we solved also this question. So last thing I would like to mention, but I will not prove that one because of time, is that we were able to show some more general result for graphs of 3 depth at most k, and we show that they are 1/k flexibly k choosable. But this is part that I will not have time to show you today. So let's move to the proof. So first we will start with proof for 2 trees. So our aim is to show that 2 trees are 1/3 flexibly 3 choosable. And as I mentioned before, our proof is algorithmic. So we will construct 6 different colorings, and we will construct them in some special way, such that those colorings will satisfy those 2 properties. And those 2 properties are good for the induction, but also the first property, which says that each color appears exactly twice at each vertex, is useful for the result itself, because if we build 6 colorings with this property, then we know that each vertex has each color exactly twice there. Then we know that at least one of the colorings has to satisfy at least third of the request, because we have 2 colors, each color twice and 6 colorings. So the requested color has to appear at least in third of them. So this is how the result is implied. And then the second property, that for each pair, which by pair I mean for each edge, the colors that are assigned to the edge in these 6 colorings are unique. So all those pair of colorings are unique. So those 2 properties will allow us to do the induction. And let me show you an example of a specific situation. So we will use, as I said, we will use the induction. So we produced this coloring with those 2 properties, those 6 colorings with 2 different properties on G without the vertex W, and now we are about to add vertex W. And we have lists of size 3, so those are the list of size 3. And this is, in this table, there are those 6 colorings. And on vertices U and V, and our task is to produce the coloring for vertex W. So this is one particular situation, but let's do it to see how it behaves. So we have colors 1 and 2. So we can try to use color C for vertex 4, for vertex W. Here we have 1, 4. So again, 3 would work. But now we have colors 1 and 2. And we know that color C was already used twice. So we need to use some different colors. So now we can use color 4. And then we have colors 2 and 4. And the only possibility would be to use color 3, but it was already used twice. So we need to use color 3 actually here. And we can use color 2 here instead, because we need to keep those properties. So here is 3 and 1. So color 4 would, okay, color 2 works also here, but we need to have color 4 for this last case. And now we produce coloring for vertex W, and it satisfies those 2 properties. So each color appears exactly twice on W, and for each pair UW and VW, the colors are on this pair are unique. So this is one particular example, and you can use this idea, let's say, to test it on computer. You can encode it in computer, and you can try all the possibilities. But you can do it, and it works. But this idea also provides an easier analysis. So let me show you how to analyze it without any need for computer assistance. So we can proceed by contradiction and minimal counterexample argument, and we will be minimizing the size of the union of lists for U, V, and W. And let's first rule out the possibility that one of the lists has unique color. So we would like to transform this unique color to some color that was already used at some of the vertices, and that's a graph with less colors on the union of U, V, and W, and hence we can apply induction, and putting their unique color only helps, like that's intuitively. And it's really the case if this unique color is on the vertex W that we are about to add. So I will skip this case just by this intuition, but let's say that this unique color is now on this vertex U, which is there, which is already colored. So we will do some more clever exchange. So we exchange the vertex, this color C, this color X, which is not on the coloring of this edge. So we will take X such as CX is not on the coloring, not on any of the 6 colorings that are already produced for this HUV. And by doing so, this table justifies that we can do it, because how the new coloring will look like. So this is now X, but it was before C. So those are the two colors that were before this C, and X is the third color of the second vertex. So as X has to appear twice, it has to appear with those 2 unknown colors, *1 and *2. So in particular, on this first column, those *1, *2 are not X. Right? It looks easy. So those *1, *2 are not X, and that justifies that we can do this swap with unique color, and we still satisfy the assumption, so we can finish coloring of W, and it's only easier. So let's now take a look how this helps. So if we split it in three situations. So now we are looking at the intersection of U and of lists of U and V, and if this intersection is of size 1, then the coloring, the list of colors on U and V has only one color in common. So there are 4 other colors that are different, and that's not possible because it means that one of the color is not on W, which has list of size 3. So there is one per color. So this implies unique color, and we already solved this case. So if the intersection list is of size 2, that's exactly there is nice property that this is uniquely determined. So those options on U and V, there is exactly one possible coloring that satisfies those two assumptions. And actually this is the coloring that we solved already on the previous page. So we know that we can finish this coloring, and there is just one option to check, and that's the one that we checked on the previous slide. So this is now easy analysis, and we can do the same for if the LU intersection LV has size 3. So it's similar case, and it doesn't. It also has this nice property that's only one case. So you need to check those 2 cases by hand, and that's it. So this is for 2 trees. I will return to 2 trees at the very end. But let's now have a look how to do those delta regular graphs. So I record the statement. We have graph of maximum degree delta for delta at least 3, and we will show that it's 1/6 delta flexible delta choosable, unless it is k delta plus 1. So first, let's justify that delta at least 3 makes sense. So if delta is exactly 2, then we can have a look at even cycle, and even cycle is 2 choosable, but we cannot satisfy on this particular example even a single request. So let's quickly have a look. So one option is to choose color 2. Maybe I will cross it. One option is to choose color 2 here, but then this is in conflict with this preference, and it cascades to all other vertices. So by choosing 2 here, we are not satisfying any request anywhere. And the same is if we choose color 3 here. So another option is to choose color 3 here, but then color 1 is forced on this right top vertex, and again color 1 4 bits, color 1 on its neighbors, and that color 2 4 bits, and so on. So again, it cascades, and we do not satisfy any request. So this doesn't work on even cycles, but surprisingly, it works for delta at least 3 if the graph if it's not complete graph on delta plus 1 vertices. So that's our statement. I should say that I will show it with, this is the slightly worse constant, because it's nicer to show and easier. So before I dive into the proof, let me recall a known structure of block-cut-tree and R-Rubin-Taylor theorem about degree-choosable graphs. So degree-choosable means that now the list sizes are not just the same, but now the list sizes are exactly, or at least the degree of the vertex. So if the list sizes are exactly the degree of the vertex, and for any such assignment we can find proper list coloring, then the graph is degree choosable. And so let's look. And R-Rubin-Taylor did a very nice characterization using this block cut tree. So what is a block? Block is a maximal to connected subgraph. So on this example, this is one block, maximal to connected subgraph, another block, and yet another block. And the characterization is as follows. So graph is degree choosable if and only if every block of G is either complete graph or odd cycle. So this is nice complete characterization of degree choosable graphs, and we will use it to provide the proof for our theorem. So our task is to build set. So we start with set R, which is the set of vertices which have a request, and our goal is to create to provide subset R prime of R. Those are the requests that we will satisfy. So remember, I will be using R prime many times. So R prime are the vertices that we will satisfy at the end. And we would like them to be at least constant, this epsilon constant times dr. The epsilon, our target epsilon from the proof is 1 over 2 delta cube. And if we will show that those R prime are the vertices that will have satisfied requests, then we will show that this shows the proof, shows the theorem. So at the beginning, we will modify R to R prime in the first step. This is on this slide, and later on, we will modify it again, and that will be the final R prime. So first, we will take vertices in distance at least 4, which discards quite a lot, but it keeps 1 over delta cubed of the original R in R prime. So this discards quite a lot of requests, but keeps at least what we needed. And this is quite strong property. So remember it, we will be using basically this heavily in the next analysis. So what we will do, we will look at this R prime, and we try to list color G minus R, this modified list. So first of all, this is R prime. Those are the vertices with request, and this is the greatest requested color. And we first cross out this color from its neighbors, and the same for this other requested color green. We also cross it out from its neighbors, and then we look at this G minus R prime, and this now has a list of the vertices. The size of the list is at least the degree of the vertices. So we can try to use list color G minus R prime and use R-Rubin-Taylor's characterization that I showed on the previous slide to show how G minus R prime looks like. So if all the components of G minus R prime are degree choosable, so all those components, all those blocks in all those components are not composed out of blocks that are either complete or odd cycles, then we are done, because we list color the rest, and then we can return back those vertices from R prime, and as those colors were discarded on their neighbors, then we can use the requested color for the vertices in R prime, and we are happy and we won. So we need to examine the case. What happens if the G minus R prime contains some bad components? So by bad, I mean those components that doesn't satisfy the Erdős-Rubin-Taylor characterization. So there are two options. Either those components are just single blocks. So those are two possibilities. So either complete graph or odd cycle, because now we are speaking about single blocks. So in case of complete graphs, if we combine, we will look at the neighborhood, and then there must be at least one vertex in R prime, because we needed to lower the list sizes of those vertices, because otherwise they have one spare color if they don't have any neighbor in R prime. So they have to have neighbor in R prime, and it has to be one vertex because of this distance condition. Okay, there should be 4. Anyway, so it has to look exactly like this, but this is k delta plus 1, which is forbidden. So this is k delta plus 1, and it's forbidden. So it doesn't look like that. The other option is odd cycle, and it has a similar analysis. Again, each of those vertices has to have at least one neighbor, because otherwise one neighbor in R prime, because otherwise those will have spare color to choose in list coloring. And by this distance condition, we will derive that at least 3 consecutive neighbors will have the same neighbor in red vertices, and this gives us again contradiction with the degree of this vertex. Because so now let's have a look on the situation when the component is more difficult. So the component has has at least 2 blocks, and now again by those conditions we will derive that there has to be at least 2 vertices in R prime that are adjacent. Each of them is adjacent to some leaf block of the component. And here comes the second modification of R prime. So we will make R prime of half of the size as before. So now because we will return one of these vertices that are neighbors of this block, we will move it back to the block. We will remove it from R prime, and this will make together a new block of block decomposition, but now this block is not complete graph because this edge is missing. And I omitted some of the details here, but basically the analysis is along this line, and it's not much more complicated. So if you would have 5 more minutes or maybe 10 more minutes, we can do it with all the cases and all the possibilities, but everything is along this line. So if we have 2 or more blocks, we have at least two vertices in R prime, and we can discard one of them and put it back, and it creates a block which is not complete graph or odd cycle, and therefore this component by Erdős-Rubin and Taylor is is degree choosable, and that therefore we can use the requested colors on modified R prime. So up to some small details that this shows to prove that I promised. So let's have a look at open directions. So it is open to it is open whether K3s are flexibly K+1 choosable. I would say that they should be, but we tried to prove it and we haven't managed. Even for K-path, it's open. So, and even for K-path of size 4. So let me show you what is K-path. So this is interval representation of K-path, of 4 paths in this case. So those lines are vertices of the graph, and edge is there whenever the vertices are on the same parallel. So whenever the vertices are on the same point or on the real line. So this is just one simple graph like this, and this is a subset of 3 trees. So on this right hand side you can see a 3 tree which corresponds to this 4 path. So we started with U, V, W vertices. Those are those 3 vertices, and then we added vertex A, which is attached to U, V, W. This is this vertex. And then vertex B, which is attached to V, W, and A. And so on. I haven't continued in this representation because it would be messy, but you can imagine how it's later. So each vertex is attached to a triangle this time. So those are actually 3 trees. And so even this simple graph, we don't know how to do it with 4 colors. So that's one open question. And another open question is to seek the characterization of graphs that are flexibly degree choosable, because, for example, diamond graph is not flexibly degree choosable. So here is an example of diamond graph, and by Rescherben-Taylor, this is not a complete graph. This is 2 connected component. So this is block. It's not complete graph, not odd cycle. So it's degree choosable, but it's not flexibly degree choosable. If you pick color 1 here, then you cannot satisfy those requests, and you need to pick colors 2 and 3 on this edge, and therefore you cannot satisfy this request. So for each possible choice you can check it. You will never satisfy any of the requests that are there. So diamond graph is not flexibly degree choosable, but where the actual characterization, if it's nice or not, we don't know, and it might be nice to look at it. Okay, that's it. Thank you for your attention, and I'm happy to answer questions if you have any.
Thanks a lot. Maybe on 3, 2, 1 we can unmute ourselves and clap. So 3, 2, 1. Yeah, very nice. Are there any questions? Okay, I have actually a few came to my mind when listening to you. So in this last open question about K3s, K+1 choosability, flexible, is it obvious that, for example, they are flexibly K+2 choosable or K+10 choosable?
Yeah, K+2, they are always K+2. This is because they are degenerate. They are degenerate, so this K+2 bound applies.
Okay, good. I see.
So like this whole
Indeed.
play was just for squeezing one. All the time we are trying to squeeze one, but it's sometimes quite difficult.
Yeah, because there is this big conjecture about degeneracy that is. So about this conjecture about degeneracy, would it also help if you knew a little bit more about the ordering? So because you know that the degeneracy is D, but for instance, if you knew that some other parameter, I'm particularly thinking about the weak coloring numbers of this is bounded. Yeah, and I don't want this to appear in the choosability, but I can allow the flexibility to depend on this. So, for example, a result would be, I don't know, 1 over the weak coloring number 2 flexibly degeneracy choosable, degeneracy plus 1 choosable. Would this make sense and would it help?
Yeah,
This could help, for instance, in planar graphs, right? Because you probably can make a degeneracy ordering with some additional weak coloring properties.
Yeah, so usually we don't care much about this constant before. So we mostly care about the size of the list, and this constant is like secondary thing.
Yeah.
So like that was also the setup that we had in mind. So usually I am pointing them out because in our proofs we were able to squeeze it into very low constant. So and in particular in those three trees it's so best possible. In two trees is best possible, but in general it's much harder to squeeze the size of the list.
Sure. Yeah.
So yeah. Like speaking about the coloring number, we had the bound for 3 depth. So there we were able to do and to do bound for general 3 depth of size at most k. But that's much easier than those two results. Okay, maybe of the same difficulty as the results I showed you.
Okay.
But it's not.
Okay, but it is not apparent how bounding the weak coloring number could help in the general degeneracy question.
Yeah. It is not like. In fact, I put a note that I should look at those sparsity parameters and if they help. So I had this in mind, but I haven't had time to explore it.
I guess there can be some opportunities in the future. Good. Are there any more questions, Tomáš? Okay, if not, then thanks again for the talk.